It's showtime. Hey guys, what's going on? Memes here. So apparently while preparing to do a video to attempt to explain free will via the Unruh effect to accelerate, it really wasn't adding up. But then I came across a lecture. I think this may have been at Stanford. Apparently, Dr. Unruh was giving his thoughts on general relativity. I thought it was fascinating. Take us away, Doc.
First one I want to say is that black holes form.
This is important.
So there's been a steady stream over the last 30 or 40 years of people who continually talk about, well, perhaps black holes don't form. We have people like Mottola, Visser.
Now, specifically, here's the thing. We're going to save that there right now because we got a bunch to cover. I'm going to do it as quickly as possible. But ultimately, it's like, what's happening?
And, locally, one doesn't know that whether that is the apparent horizon for a black hole or is one of these stupid apparent horizons which mean absolutely nothing in space-time, because that basically depends on whether or not this apparent horizon actually closes off on itself.
Apparently, with the Unruh effect, the whole thing is, as long as one is accelerating, you can essentially kind of outrun a photon, potentially, at least for a little while. As long as you're under constant acceleration, you're going to need to end up going really fast, but essentially, it changes the temperature, apparently, relatively. And I'm like, wait. So what you're saying is you could ultimately, potentially outrun the cosmic wave function? If you're not interacting before, does that mean... Is this why people like to go fast? Because, we seem more free? I'm just saying.
And that's a very non-local question. And all this matter doesn't have time to know that non-local question.
Oh.
But furthermore, if one looks at the stress energy tensor, the effective stress energy tensor, i.e. take G mu nu, calculate G mu nu, and look at what T mu nu is, one gets this horrendous acceleration.
Oh.
In other words, I've got a solar mass body that's collapsing at the velocity of light as it nears the horizon, and it stops within a Planck time.
That is it. I remember Professor Wolfer was talking about the snap, the crackle. You had jerks, snap, crackles, and pops. Those aren't just Rice Krispie treats, the name of the elves. I'm just saying that is an actual thing. I meant to look that up. I feel like this might be relevant. Continue, sir.
Well, f dx, equals 1/2 v squared if dx is the Planck scale.
Oh.
And sorry, there's an m in there.
Mass or something.
Then f has got to be absolutely huge.
Oh.
What kind of f could that be? Could it be a radial pressure? Could this thing start emitting radiation? Like sometimes they talk about the interaction of this stuff with Hawking radiation or the acceleration.
Quick thing, essentially the Unruh equation is basically the same thing, except you replace, was it the F or something, with G, the gravitational constant. It's fascinating. Why is it the same? These are fascinating questions.
Radiation near the black hole. Well, the trouble with any radiation is if it's outward going positive radiation, which it should be if it's going out, that's going to push it more. That's the wrong
it's like
force.
A Chinese finger trap.
If it's inward going positive radiation, that's going to stop this. But of course, that just dumps the energy into the black hole even faster. So that doesn't work. It could be outward going negative radiation. But of course, outward going negative radiation, which then would give a pull on there, that negative radiation would get out to infinity, and we could bathe ourselves in negative radiation and violate all kinds of laws of thermodynamics. We wouldn't have to worry about thermodynamics anymore.
Oh, so only if we consider thermodynamics to be important, perhaps this is important. Oh, welcome, Angel. Thank you, my friend. We need to do a stream soon. I'm trying to start up my interview series again, so if you want to pop by, totally love to have you. Okay, where are we? The next part right here. Okay. I'm going to go back over to this screen. I'm going to do right... Oh, wait, I need to add it back in. There we go. All right.
at the point at which I switch on the sponge, i.e. A and B and C are switched on from 0.
Essentially, something to potentially catch the radiation. Think about like one of those like hefty, extra heavy-duty paper towels or something. That's the analogy, except for like the power cosmic or something.
I suddenly get this loss of coherence between the radiation given off by the sponge just afterwards and the radiation that's traveling in the space-time before, and I basically get this firewall.
That's like a barrier.
Of positive energy radiation. Well, in fact, it had better be positive energy radiation, because if there was vacuum inside, this is all negative energy, and we know that the total energy
Looks like
integrated
there's a lot of
over a
stuff
complete
going on
slice, it
there.
better be equal to 0.
Must be a fancy
So
articulation.
these guys give off these massive positive energy fluxes.
Oh.
If I now boost this so that this occurs way back at the initial, at t equals minus infinity, then I find the singular delta function squared, at least singularity in the stress energy tensor, traveling just along this past horizon.
Oh.
And I get a firewall. And that firewall is arising precisely for the same reason as the firewall arises in all of the discussions, because there's this loss of coherence, this loss of entanglement.
So it kind of sounds like he's saying there appears to be some form of an informational boundary, if you would, where there's no longer communication. Whatever's happening in there happens is in there. What happens outside is outside, and just never shall the two meet until they do. And what happens?
Between the radiation that's given off by the sponge after it switched on versus the radiation that was there before it was switched on.
Huh. How very fascinating.
In fact, I've come to the conclusion that firewalls are, in fact, almost ubiquitous. Let's ask another question of the same kind of model.
I love this. Like they're in the doobly-doo.
I go ahead and I put now not a firewall, not a sponge, but just a mirror. So this is just a delta of x, phi squared delta of x, and we notice that that obeys that AC minus b squared equals 0, because c is 0 and b is 0.
Oh. That sounds like a point, potentially.
What happens? I now want to ask the question about the Hartle-Hawking vacuum.
Huh.
Does there exist a Hartle-Hawking vacuum for this?
An interesting
Now,
question.
one of the assumptions that gets almost universally made is, yeah, of course. I mean, Hartle-Hawking vacuums, they're just the equilibrium state.
That sounds like balance.
But we notice that there's a problem even with the equilibrium state. If that internal guy emits radiation such that the outside world is still in thermal equilibrium, we nevertheless get the singularity along the past horizon. And the answer is, although I haven't been able to completely prove it, is that remember, this situation is completely boost invariant.
Boost invariant. Is it possible that factorization may allow us to model that in a coherent way? Maybe using some Planck units? Continue.
That there exists no state which is regular along both horizons and is boost invariant.
So,
i.e., typically one gets this firewall occurring along, for example, the past horizon, but it can equally be along the future horizon. If one puts an exactly symmetric mirror on the other side, then I suspect that there is a regular state. Again, I haven't been able to prove it. If one makes this mirror slightly weaker than this one, again, you have trouble.
So what it's sounding like the good doctor is talking about is, let's say hypothetically you go into a black hole, assuming you could do that. Go in there. Once you're in there, what going on with the outside? Does it look like there's anything going on? Is there This is starting to sound like a lot of stuff people have talked about before, but I think it's actually even more fascinating. So that was that. So we're gonna go over here. Here we go. All right, go back over here. All right, good doctor. What are we out? There we go. What do we got going on, my friend?
That in fact, Jim Bardeen has recently been thinking a lot about the whole firewall issue and black holes. And one of the ideas he came up with was, let's assume that at the center, at the singularity isn't really a singularity, but is some finite point in space.
Oh, that sounds like a point. Only we had something that might help us model such a complex thing.
So instead of 1 minus 2m over r,
this is from like 2013 apparently, as opposed to 2016. Just reference.
We have the central metric
Science
looking something like
along.
this.
All right.
This is a metric that when r is very small, this term dominates, and this is just 1 minus r squared over a squared, which is de Sitter space.
Cool.
So a could, for example, be of the order of the Planck scale.
Oh.
M is the mass of the black hole.
Hmm.
And if we write this in retarded coordinates,
That's the technical term.
Minus r squared d squared.
It's basically, it's
if we write this in our
function.
retarded coordinates, we can in fact get a solution, a nice solution with null radiation just by making that mass be the null coordinate v, depend on the null coordinate v. This is basically the Vita metric, and it's got a bunch of energy coming in towards the black hole. And if we make that energy flux negative, which you expect for a black hole, then this thing will gradually decrease this value of m as though we were evaporating the black hole.
And again, I'm kind of agnostic. I could go either way. I have my own thoughts about why black holes may not really evaporate, just because if they can absorb energy, if there's energy in the vacuum. Again, I'm just saying, but we're gonna pop ahead just a wee bit more, and here we go. All right, so 110.
Yeah, I'd just like to stress that even if we didn't go in and mine, all of these high L modes have some probability that's not zero to tunnel through the angular momentum barrier.
Yes.
So their wave function is going to develop a tail outside of the black hole. And if we assert that these are in the Hawking state in the infalling vacuum, then that alone would destroy unitarity, if only by a little bit.
I don't mind unitarity being, I don't think there's anything terrible about unitarity being destroyed.
I mean, that's just a fascinating thing, because so many people are like, we need unitarity. Apparently, that's something you said at another point here. But this is great because the response.
I know, but why did you give such a long talk in that case? I mean, if we don't worry about unitarity, there don't need to be firewalls. That's it.
So, fine.
Just like, all right, fine.
You just summarized my talk, although I did say a few other things along the way. But.
So,
yes.
In response to
and my whole thing is with us. Wait. So what you're saying is there's a boundary where stuff and things may be going on, but we don't necessarily know what's going on. The information is there. We just don't necessarily have it yet. But we'll finish up with
last
this.
interchange. I wanted to mention that that's the kind of model that, for example, I have been exploring, where the information is emitted further out than right at the horizon. And I actually think that there are models that evade at least the objections I've seen that come from the mining Gedanken experiments.
Yes,
and I'll talk a little bit more about those on Wednesday. But basically, you can have extra interactions that only excite information carrying excitations going out when you are mining, and when you're not mining, they're not excited. So more on that later.
I mean, is that a measurement problem? Kind of sounds like a measurement problem. I don't know.
Okay.
I had a question.
I'm sorry I won't be here.
I had a question
Hold on.
about your final model that you presented.
It's a
If I understood
combination
it
of other
correctly-
ones. Well, we're going to skip ahead just for time being because I'm late, of course. We go to Professor Leonard Susskind.
Yes.
First of all, thank you for some extraordinarily interesting examples of very interesting things. I really love them. In particular, I love the example of the decoherence without energy violation. But I think if
Yeah.
I had seen these particles come and collide and do that and conserve energy and decohere in this way, my guess would be there's a spin somewheres. And that spin somewheres is
A rotation, some may
containing
say.
the information about, I would guess that
Sure.
somehow, and I would be right in your case.
Of course.
So I am guessing then if I were to see the same thing outside a black hole, I would guess that I would guess there are microstates of the black hole
Links in the doobly-doo.
containing that information. So what I'm saying is your example is a beautiful example
Sure.
of what though?
Professor Susskind, that's a great thing. I'm not necessarily sure even Dr. Unruh knows what's going on, but here's the response, and it's a beautiful thing.
There certainly when the matter falls in, if there's a singularity, then all of the information, all those microstates in the
Perhaps a
matter just fall
particular
off the singularity.
articulation.
The what? The microstates. of matter,
Microstates
yeah,
of the
okay.
matter, etc., simply fall. All the information just falls off the singularity. The black hole doesn't notice this. It doesn't care. It still behaves in exactly same way. If instead of having that singularity in there, you had some sort of baby universes branching off so that all these microstates went in there, that also wouldn't make any difference to what's going on the outside.
Is it just me, or did he just casually throw out, yeah, so basically if we're creating baby universes, is that what some folks refer to as like the multiverse? I've taken more to it's like e pluribus unum, out of many one. The universe is the one. So it's just, I'm just saying it would be encompassing. Call it what you want, however you want to model it. But this was just a fascinating exchange.
Well, okay, but the black holes,
In other words, what's going on inside really doesn't matter as far as the behavior of the black hole.
The black hole has to somehow record in a way that has a memory which of the states.
No.
Well, all right, but
why does it? All it has to remember is there's a mass and angular momentum.
I'm just arguing by example. The example being yours. That spin is the thing which remembered.
In the case of the black hole, the matter itself remembers its own state. If it falls off a singularity, that's the end of it. Where this information is recorded, I don't know, and I really don't care.
Okay.
I'm saying that the behavior of the black hole is independent of, I don't care, not because I'm just so perverse that I don't care, but because the behavior of the black hole is independent of where and how that information is recorded.
Okay, so
where, it's somewhere inside, it's inaccessible, and that's all that matters.
The only last comment is that a good part of the reason that we believe what we believe is by examples that have come from things like ADS-CFT, from matrix theory and so forth, where we can't just dismiss those. A black hole in space, right?
Agreed.
Okay.
I mean, ADS-CFT is something that
basically he's not really familiar with it. He's like, I'm not enough of an expert. I'm paraphrasing here to really give it a good look and be like, oh, this is the truth. Because what's going on? We're trying to decide what's behind a potential firewall. Perhaps some boundary of persistence here. Why do I say this? Because we go back to our friend Thad Roberts here. A quick little online publishing of his a quick reading of 44.
Another baked-in consequence of the minimal arena's external shape is calculus.
I like that term.
In addition to the fact that the generalized power series of the external domain's hyperbolic connections, e to the x, defines the elementary derivative sequence.
That's factorization.
Every term in this series defines the derivative of the following term.
I hear it's useful.
The derivative geometrically defines how the volume of an n-dimensional hypercube increases or decreases as the side length of that hypercube is changed. On the other hand, integrating this picture or stacking the faces geometricizes the fundamental
like
theorem of
something
calculus,
Mathologer
building a
did.
decomposition of the n cube into n pyramids, which is a geometric proof of Cavalieri's quadrature formula.
Oh,
What the
sounds like
minimal
explains
arena's
things.
external projection looks like depends on the scale we focus on. On its grandest scale, which is very specifically 1.4167869859079
It's the
times 10
blank
to the
temperature
32
expressed in meters instead of Kelvin.
the n hypersphere of maximal volume defines the simplest possible geometric form in S3, the great sphere, minus its boundary. On its smallest scales, between 1.8755459671396 times 10 to the negative 18 meters and 2.1764268 times 10 to the negative.
So that kind of looks like a magnitude that's, I don't know. Is that Planck charge or elementary charge? Something like that. And oh, that appears to be on a scale of the Planck mass, except in meters. Now, again, I'm not saying that this explains everything. Hey, I'm just a dude on the internet. But when I look at stuff like that, and then I click other things like this, I'm like, oh, we go to our friends at Wikipedia. Again, just a first level approximation. Here's a strong interaction. Strong interaction or nuclear force is a fundamental interaction that confines quarks into protons, neutrons, and other hadron particles. The strong interaction also binds neutrons and protons to create atomic nuclei, where it is called the nuclear force. Most of the mass of a common proton or neutron is the result of the strong interaction of energy. Oh, because remember, E equals mc squared, yada yada, plus a couple other things we don't always pay attention to. Just saying that I think they're important. The individual quarks provide only about 1% of the mass of a proton, in a range of 10 to the negative 15 meters, slightly more than the radius of a nucleon. The strong force is approximately 137 times as strong as electromagnetism. Oh, I think we get that from the fine structure constant. I hear it's important. 10 to the 6 times as strong as the weak interaction, and 10 to the 38 times as strong as gravitation. That's a fascinating scale there. But you look at this, I'm like, all right, it's like 1 femtometer. It's really freaking small. You see, it's like, all right, well, those are 2 hydrogen atoms. But basically, they seem to be bound together there. And that approximation of a helium atom, yeah, they're fused. The strong interaction is observable at 2 ranges, mediated by 2 force carriers. On a larger scale of 1 to 3 femtometers, the force is carried by mesons that bind protons and neutrons. Nucleons together form the nucleus of an atom. On a small scale of about less than 0.8 femtometers, the radius of a nucleon, the force is carried by gluons that hold quarks together to form protons, neutrons, and other hadron particles. In the latter context, it's often known as the color force. Blue is the best flavor, in my opinion. The strong force inherently has such a high strength that hadrons bound by the force can produce new massive particles. Thus, if hadrons are struck by higher energy particles, give rise to new hadrons instead of emitting freely moving radiation. Gluons, the property of the strong force is called color confinement, prevents the free emission of the strong forces. And in practice, jets of massive particles are produced. Now, again, I'm not saying that maybe some external boundary that helps provide balance or something like that, maybe what's binding things together, but wouldn't it be frickin' sweet? Again, that's going to require a lot of experimental evidence and a lot more smart people than myself. Again, I'm just a dude on the internet that happens to have yet to have proved...
It's turtles all the way down.
Thank you, Professor Wolfram. But that's all I got for right now. Well, peace out, everybody. Be safe. Take care of yourselves. You never know what tomorrow may bring.
Have you guys checked out the Memes of Destruction's channel? He's an interesting dude. I